Example 2.8. Okay, so here we have a volume charge distribution in the shape of a sphere with the radius of A. Okay, so here the volume charge distribution is given as rho V with the unit of coulomb per meter cubic. Okay, so here we want to find the electric field at the distance r from the center of this sphere. Okay, okay. So I'm going to change to the whiteboard now. Okay, so here I have the question rewrite in this whiteboard. So this is the charge distribution, volume charge distribution in the shape of a sphere with the radius given as A. Okay. Okay, so here we have the charge density given as rho V in coulomb per meter cubic. Okay, so we are going to find the electric field at a distance r from the center. Okay, so here we will use, of course, the Gauss law. Okay, so we'll start with the Gauss law first. As usual, the equation is given as E dot ds is equivalent to QENC uh, over epsilon 0. Okay, so first, what we need to do here, this is a volume charge distribution. So it doesn't state whether it is a positive charge or negative charge. So here, as usual, we will assume that it is a positive charge. So if it is a positive charge, then our electric field or will be in the r direction, meaning that here this is a positive charge, so it will be source for the electric field. Okay, so if you want to draw that, okay, so we are going to draw the electric field. Okay, so as usual, you have to think this in three-dimensional, although here you can only see it in two-dimensional. Okay. Okay, so now we can write the electric field, okay, which we later use in solving the vector for this Gauss law using this. So here the electric field is in the direction, is radial direction pointing outwards. So here E will be E, the magnitude, and the direction is given as R. Okay. Okay, so here what we need, another thing that we need is the closed surface. So here the closed surface, the appropriate closed surface for this one, a symmetrical closed surface will be a sphere, of course, because since we have a spherical charge distribution, a sphere will enclose all the charges over here. Okay, so here the closed surface will have the radius of r, which is our point of reference. So we'll go back to okay, so here let me draw the circle for the closed surface first. The closed surface over here is sphere. Okay, so here we are choosing sphere as a um, symmetrical shape that is enclosing the whole charge distribution. Okay, so here the radius of this closed surface will be based on our point of interest. So here our point of interest is at a distance r from the center. So here the radius for this closed surface, so radius is r. And apart from that, we also need the normal direction to this one. So to determine the normal direction to this closed surface, first we um, um, choose a random smaller surface area, which is ds. Okay, so and 90 degrees to that will be pointing to outward direction in radial direction. Okay, so here ds, the vector, we can rewrite that as ds in r direction. Okay, so we are going to use this information and also this information to solve the dot product for this Gauss law on the left hand side of the equation. Okay, the left hand side of the equation. So here we have left hand side. Okay, so here first of course we have to deal with the dot product first. So now we already know that P as shown before is in r direction, and for ds is also in r direction. So here we have the dot product between r and r, so that is equivalent to 1. So s e ds. Okay, so I'm sure I don't have to repeat this process over here where we have the dot product between unit vector r and also unit vector r. Okay, so here the integral is a surface integral, so we don't have to consider the electric field for the integration. So s ds. Okay, so and then from the previous chapter, you already know that integral of ds will give you the surface area. So in this case, this will be the surface area of the closed surface. Okay, so here the closed surface is a sphere. So the surface area for a sphere with radius r is 4 pi r squared. Okay, so now we can rewrite this equation. Uh, E dot ds equal to q e and c over epsilon 0 to okay, so here we already simplify the left hand side of the equation for the Gauss law.